So next I want to explain the brain changes that go along with perceptual learning. So this chapter is about habituation, sensitization, and the third is perceptual learning. So in perceptual learning, repeated exposures to a stimulus lead to improved ability to recognize or process that stimulus. That's what we're really talking about. So the question is, how does the brain get better at processing an input? Well, how does it process an input anyway? So what you need to know is that for people, for humans, the input from each sense is relayed to a specialized sensory cortex. It's in the parietal lobe. You can see it here. The parietal lobe, it's called the primary somatosensory cortex. All right, and then you have it blown up right above it. And then you have a bunch of parts that don't actually all seem like they make sense because they're not all next to each other. But basically, the different parts of our body are have a corresponding part of the brain that processes these sensations from them. So you've got well, genitals. The sensation from the brain is sort of in the middle of the brain, but deeper in for genitals. The toes, the foot, leg, neck, head, arm, etc., etc., etc. Okay, so you can see here fingers. Fingers are right here, but the each neuron within the sensory cortex has a distinct receptive field, part of the world it responds to. So if you talk about, touching a particular part of your lip, well, I touch the upper lip, there's a neuron or set of neurons around this region that are sensitive to that touch. So they're firing when I'm touching right here. And these receptive fields are well organized in the cortex and they form orderly maps. All right, so these maps, we know that they are orderly, but we know that they're not actually fixed. They actually can change with development and experience. And so that's what they mean when they talk about cortical plasticity. Cortical plasticity is how the receptive fields of neurons of the sensory cortex can change due to development or experience. And we know that even with just a small amount of practice, it can actually temporarily rewire these maps. And if you have repeated practice over time, these maps can change permanently. So how do we know that? Okay, there's a study. It's called two-point discrimination. It's where we touch the fingertip with either one or two tiny pins. They're not like they're not going to cut the skin. They're just really like toothpicks. Just got a little bit of a point to them. And they have the participant report if he or she feels one or two pins, and their eyes are closed or covered. So the task is they're going to touch them with either one or two pins, and they are to report, well, do you feel one pin or two pins? All right, and if they can truly feel the correct number, then they're going to say the right answer 100% of the time. If they can't, then they're only going to be right 50% of the time. And so they're measuring the smallest distance where the participant is reliably correct. Okay, but it's really not about how well they do on the test. That's not really what they're interested. They're interested in the mapping of the brain and the activation of the brain while doing this task. So they can actually put people in a scanner as they're doing it. So they have a baseline measurement of sensitivity with the fMRI scan. So they do this a few times while the scanner is going, and they have the person sort of feel out the pins and see if they can detect it. Then they have 2 hours of training, and they do it with the right hand only, and they do repeated trials with feedback, and they tell them if they're right or wrong. Okay, the post-test, and then what they do is they do a post-test and say, okay, how sensitive are they? And they do the fMRI scan. Okay, so here you can see before and then after. And I don't know if you could see really well, but you can tell that there's the yellow regions are actually more active. And let's see here. And so I believe this is the person's right side of the brain. Well, so we're more interested in the left side of the brain because this is the right hand and the left side connects to the right hand. Okay, so what we see is that there's much better sensitivity in the trained hand. That's just shows that their capability increased. So if they practice, the hand that they trained with is going to be much better. And what they find is that the activation in the right finger area, the somatosensory cortex, has increased activation. All right, and the slides have the double exclamation point because isn't that cool? It shows that the brain has adjusted with experience. It's now differently activated with experience than it was before. Again, same person, but their brain is now operating differently with experience. So again, we have this idea, oh, our brain, it just does what it does. Now this shows that even in 2 hours, you could see the difference of practice in 2 hours on how active the brain is, which is, again, pretty remarkable. So the experiment shows that just 2 hours of practice can rewire the cortex. Now, these changes are temporary. The next day, the sensitivity was back to normal, and so was cortical activation. So that's kind of the bad news of this, is that just 2 hours of practice won't permanently change your brain. But if you did repeated practice over and over and over and over again for days and days and days, that that ability to detect the difference between 1 and 2 pins and the actual activation of the brain can actually become more permanent. So again, this is the thought, is that you get some changes on the short-term basis. Long-term, though, you need to do repeated practice to get good at it. Okay, so that is a little bit of how habituation, sensitization, and perceptual learning, this video, changes in the brain.